Today, we're talking about what is quite possibly the future of machine learning in both computer vision and NLP. We're talking about a combination of both into a single multi-modal model. That model is CLIP, which was built and trained by OpenAI. Now, CLIP is open source, and it has been around for a little while. It's been around since the start of 2021. But in the past few months, we've seen the adoption of CLIP grow at a pretty insane rate. It is found uses in a load of things. So what we will be focusing on is text or multimodal search across text and images. But we're also going to talk a little bit about zero-shot classifications, zero-shot object detection. And at some point in the future, we'll also talk about the use of models like CLIP or even CLIP itself in the diffuser models that have become incredibly popular recently, like DALL-E 2, Imagen, and Midjourney. Now, to understand why CLIP is so important, we can use a paper that was released in 2020 called Experience Grounds Language. In Experience Grounds Language, the authors defined these 5 different world scopes: corpus, internet, perception, embodiment, and social. Now, most of the models that we're aware of in NLP, this is a sort of NLP language focused paper, these were sort of the state of the art very recently. So you have BERT, T5, and all of these different models, GPT, and so on. In perception, this is where we start to see not just NLP, but also computer vision. So here is where we are now with CLIP. Okay, and quite interestingly as well, in the next world scope, this is where you start to get reinforcement learning, and then you continue going. So you almost see this culmination of all the different disciplines in machine learning coming together into one larger discipline. Now, the focus between these different world scopes is mostly on the data that is being used to train the models. So over here, world scope 1, you have the first models that we saw, which would have been things like word-to-vec, which is probably one of the earliest examples of deep learning in NLP. And that consisted of training a neural network on a small, or not small amount of data, but small compared to future data sets. So a single corpus, for example, 100,000 sentences from Wikipedia, maybe one example of that. Then going forwards, we have the internet-sized corpuses. So these are based on a huge web scraping from across the internet from many different sources. And the models trained on this were able to obviously kind of pull in more general understanding of language from purely text data. Okay, so it's a lot of data, but it's still purely text. The next one, which we're focusing on, world scope 3, is not just that. It's, in our example, text and image data. Okay, so we're training a model to understand both of these different modalities of information. And this is almost like AI moving from a purely digital, very abstract space to a more realistic, real world space. Because in the real world, we don't just rely on text data, we rely on a huge number of sensory inputs. We have visual, audio, touch, and everything else. Okay, so we're sort of moving more towards that more broad scope of inputs from different modalities. Okay, where a modality would be something like text or image or visual and so on. For us, in the real world, that chaotic ensemble of different sensory inputs is what kind of creates or trains our internal model of the outside world. So it makes sense that that is the sort of direction that machine learning and AI may also go in. So to achieve this multimodality in CLIP, we actually use 2 models that are trained to almost speak the same language. So we have these 2 models. One of them is a text encoder, one of them is an image encoder. Both of these models create a vector representation of whatever they are being input. So the text encoder may get a sentence. That sentence could be two dogs running across a frosty field. And then we have a image of two dogs running across a frosty field. And CLIP will be trained so that the text encoder consumes our sentence and outputs a vector representation that is very, very closely aligned to what the image encoder has output based on the image of the same concept. Now, by training both of these models to encode these vectors into a similar vector space, we are teaching them to sort of speak the same vector language, right? So it's very abstract. This vector language is like 512 dimensional space. So we can't directly understand or it's very difficult for us to directly understand what is actually happening there. But these two models do actually output patterns that are logical and make sense. And we can see some of this by comparing the similarity between the vectors that it outputs. Okay, so we can see that the two vectors for dogs running across a frosty field, both the text vector and the image vector, are both within a very similar vector space. Whereas something else like elephants in the Serengeti is, whether it's text or image, is not here with our two dogs running across a frosty field. It's somewhere over here, right, in a completely different space. So what we can do with that is calculate the similarity between these vectors and identify which ones are similar or not similar according to CLIP. From these meaningful vectors that CLIP is actually outputting, we are able to create a content-based image retrieval system. Okay, so content-based image retrieval is basically where we, using some text or using maybe even another image, we can search for images based on their content, right? And not just like some textual metadata or something that's been attached to them. And with CLIP, unlike other content-based image retrieval systems, CLIP is incredibly good at actually capturing the meaning across an entire image. So, for example, with our two dogs running across a frosty field, we might also be able to describe the background of that image without mentioning that there's two dogs in it. And if we describe it in such a way that we align pretty well with what that image actually is, what is in that image, we might actually also return the image based on that. So we're not just focusing on one thing in the image. CLIP allows us to focus on many things in the image. So an example of that is within this dataset that I've been using here, there are no images. There's one single image of the food, a hot dog. Okay, so I tried to search for that, and the first image that is returned is a dog eating a hot dog. Okay, so it's pretty relevant, but of course there are no other images of hot dogs in this data set. So the other images that are returned are quite interesting because in some way or another they are kind of showing a hot dog. So the first one, we have a dog looking pretty cozy in a warm room with a fire in the background. Then we have a dog in a big woolly jumper and another dog kind of like posing for the camera. So weirdly enough, we got a load of hot dog images, even though it's not really, maybe it's not exactly what we meant when we said hot dog, but a person could understand that. Okay, we can see how that term and those images are related. Now, we're not actually only restricted to text to image search. When we encode our data, when we code text and when we encode images, we are actually just creating vectors. So we can search across that space in any direction with any combination of modalities. So we could do a text to text search, image to image search. We can also do image to text search, or we can search for everything. We could use some text to search for both text and images. We can kind of go in any direction, use any modality we want there. Now, let's go into a little more detail on what the architecture of CLIP actually looks like. So CLIP, as I mentioned, it's these two models. Now, these two models are trained in parallel. One of them is the text encoder. Now, it's just a generic text encoder with 12 layers. And then on the image encoder side, there are two different options that I've spoken about. There is a vision transformer model and also a ResNet model, and they use a few different sizes for ResNet as well. Both of these encoder models output a single 512 dimensional vector. And the way that these models is trained is kind of in the name of CLIP. So CLIP stands for Contrastive Learning in Pre-training. And so the training that is used during pre-training is contrastive. It's contrastive pre-training. Now, across both NLP and computer vision, large models sort of dominate the state of the art. And the reason for this, or the idea behind this, is that just by giving a large model a huge amount of data, they can learn sort of general patterns from what they see and almost kind of internalize a general rule set for the data that it sees. Okay, so they manage to recognize general patterns in their modality. In language, they may be able to internalize the grammar rules and patterns in English language. For vision models, that may be sort of the general patterns that you identify or notice with different scenes and different objects. Now, the problem with these different models, the reason they don't fit together very well already, is that they're trained separately. So by default, these state-of-the-art models have no understanding of each other, and that's where CLIP is different. That's what CLIP has brought to the table here. With CLIP, the text and image encoders are trained while considering the context of the other modality. Okay, so the text encoder is trained and it considers the modality, or it considers the concept learned by the image encoder. And the image encoder does the same for the text encoder. And we can almost think of this as the image and text encoders as sharing a almost indirect understanding of the other modality. Now, contrastive training works by taking a image and text pairs, so for example, the two dogs running across a frosty field, and putting those together into the text encoder and image encoder, and learning to encode them both as closely as possible. For this to work well, we also need negative pairs. So we need something to compare against. So this is a general rule in contrastive learning. You can't just have positive pairs, because then everything can just be kind of encoded into the same like tiny little space, and you don't know how to separate the pairs that are dissimilar. Okay, so we need both positive and negative pairs. So we have a positive pair. Okay, in order to get negative pairs, we can essentially just take all the positive pairs in our data set, and we can say, okay, the pair T1 and I1, we can mix T1 with different I's. Okay, so we can do T1 with I2 and I3, I4, and so on. So we're basically just swapping the pairs, and we can understand that those other pairs are probably not going to be similar, as long as our data set is relatively large. Occasionally, maybe we will get a pair that are similar, but as long as our data set is large enough that doesn't happen too frequently, it's not going to affect our training. It will be sort of a negligible problem. So with this idea, we can use a loss function that will minimize the difference between positive pairs and maximize the difference between negative pairs. And that will look something like this, where we have our positive pairs in the diagonal of the similarity matrix, and everything else is something that the dot product there, we need to maximize. And this image that you see here is actually the pre-training for a single batch. Okay, so one interesting thing to note here is if we have a small batch, say we only have a batch size of 2, it's going to be very easy for our model to identify which 2 items are similar and which 2 are not similar. Whereas if we have 64 items in our batch, it will be much harder for our model, because it has to find more nuanced differences between them, and basically the odds of guessing randomly between those and guessing correctly are much smaller. So a larger batch size is a good thing to aim for in this contrastive pre-training approach. So with that, I think we have a good idea now of how CLIP can be used, and also how it has been trained for this. So what I really want to do now is kind of show you how you might be able to use it as well. Now we're going to be using the Vision Transformer version of CLIP. Okay, so remember I said there's the ResNet and Vision Transformer options for that image encoder. We're going to use the Vision Transformer version, and OpenAI have released this model through the Hugging Face library. So we can go to the Hugging Face library and use it directly from there, which makes it really easy for us to actually sort of get started with it. So let's go ahead and do that now. Okay, so for this we will need to pip install a few libraries here. So we have transformers, torch, and datasets. So datasets, we need to actually get a dataset. So I've prepared one especially for this. So we have this image to text dataset, and in here we don't have, there's not much, it's just 21 images or text to image pairs, and we can see what they look like. So we have this text, aerial shot of a futuristic city with a large motorway. Okay, so I tried to just describe this image as best I could, and yeah, that's what I got. And there are, like you saw just now, 21 of these image to text pairs in there. So let's go ahead and actually prepare or download and sort of initialize CLIP for our use. So the model ID on Hugging Face is this. So if we were to go to huggingface.co, we could type that in here, and we have the model there. Okay, so this is the model that we're using over from OpenAI here. And with this model, we use these two. We use a processor and a model. So this is the model itself. This is CLIP, right? This is almost like a pre-processor for both our text and also the images. Okay, so one thing we'll do here, if we have a CUDA device available, we can move our model to the CUDA device. At the moment, if you try and do this with MPS, so if you're on Mac and you have Apple Silicon, there are some processors or some transformations in CLIP that don't function on MPS at the moment. So I would stick with CPU. We're only doing inference, so it's still pretty fast. Now, as I was mentioning, the processor is what handles both the text and image preparation. That needs to happen before we feed them into the actual encoder models themselves that make up CLIP. So for text, we do this. So this is going to work like a normal text tokenizer. A normal text tokenizer for text transform models is used in order to translate our human readable text into transformer readable IDs. Okay, so we pass the text here. We make sure we are saying there are no images included here, because the processor, if we have both images and text, it can process them at the same time. We can do that here as well, but I want to show you it separately just to show you what they're actually doing. So the padding, we need to set that to true, and that is because different sentences can have different lengths. Okay, so you have like hello world and whatever I wrote before up here. So this aerial shot of futuristic city, aerial shot of a city. These two sentences have different lengths, and a transform model needs to see the same length being input for all of the text that is within this sort of single batch. So basically what it's going to do there is add what are called padding labels. So it's just going to add a few of these up to the length of the longest sequence within that batch of text items. Because in here we have those 21 sentences. So that's all we're doing there. Not sure what that is. And then we are returning those as PyTorch tensors. And then finally just moving them to whichever device we're using. I'm using CPU here, so it's not actually necessary to do this, but I'm doing it in case you do the same on a CUDA enabled device. So from there, we have these input IDs and an attention mask. Okay, so let's have a quick look at what those are. So if we go into tokens and we have a look at input IDs. Okay, you see we get all these literally just integer values. And you'll see that a lot of them have this 49407 at the end, right? They're the padding tokens there, okay? So they are not represented as strings, but they're represented as these integer numbers, okay? And we know that they're the padding tokens because they're appearing several times at the end of each sequence, and none of the sequences I fed in there they didn't have any similar words at the end of those, okay? So you can see them all here. So we know that those are the padding sequences. We also see there's like an initialization of sequence token there as well. And then everything in between those, they are tokens that represent a word or a part of a word from our original text. So that's the input IDs. The attention mask is, you'll see, so here you can see that it's just these ones and zeros. Now, the ones represent real tokens, okay? They represent real words that were in our from our text inputs. The zeros represent where our processor has added padding tokens. So this is used for the internal mechanisms of the text transformer to know which tokens to pay attention to, which ones to ignore, because we don't want to really focus on those padding tokens because they're meaningless. They're just there to make sure we have the same size inputs going into our transform model. That's all that is. So we can go down, and after we have our tokens, what we do is we use CLIP to encode all of them with this get text features. Okay, and then we pass our tokens, and I've got two devices here. I think I already moved them to device, so I don't need to do that again. We can actually remove that. Okay, and okay, what do we get here? So we get 21, so 21 text inputs, that makes sense. 512 dimensional vectors. Okay, so they are our text embeddings representing each of those text sentences that we just gave. And then one other thing I wanted to point out here is that we have the min and max values, and they're pretty big. Okay, they're clearly not normalized. So this depends on what you're doing. If you want to compare these vectors, you need to make sure you're not using a similarity metric that looks or that considers the magnitude of your vectors. You need to only consider the angle. So you can do that with cosine similarity. Or the alternative is that you can normalize these vectors, and then you can also do this with dot product similarity. Okay, so to normalize, if you wanted to use dot product similarity, you would do this. Okay, so here we're just detaching our text embeddings from the PyTorch graph, moving them to CPU if needed. We actually don't need to do that, but do it here anyway, and convert them into a NumPy array. And then we calculate the value that we will normalize each vector by. Okay, so for each vector, we're calculating a number, and then that number is what we're going to divide them all by here, okay, to normalize that. And then after that, you can see the minimum and maximum is this minus 0.15 and plus 0.53. Okay, so neither of them going over -1 or +1 now. Now, when it comes to encoding images, we do the same thing, or very similar thing. So images are also pre-processed using the processor, as we did with our text, but we just use slightly different parameters to start there. So the reason we're processing these images is that CLIP expects a certain size of image when we're feeding images into it. And it expects those image pixels to be normalized as well. Now, RGB images by default, the pixel values in there will range from 0 to 255. We need to normalize those, and we also need to resize the images. So you can see that here. So the first image, it has this size. It's a pretty big image. Okay, this is the width and the height of that image. Now here we're taking all the images and we're processing them. Make sure we say text is none, and that will actually only output one tensor, the pixel values tensor. So we're just going to extract that straight out there, and we're also going to move it to the device, set hardware device, in this case just CPU. And now let's have a look at this image, or images now. So now we can see that we have this this array or tensor with 3 color channels. So this is the RGB, and it has a height and width of 224. So it's been sort of squeezed into a smaller size now. And we have 21 of those because we fed in all of our images. Okay, so this is how we use the processor, and this is just resizing and normalizing our images, ready for the vision transformer encoder of CLIP. And very similar to before we used get text features, now we're going to use get image features, and we pass in those images like that. And again, as you might expect, those images are not normalized. You see that here. And as we would also expect, they are the same dimensionality as our text embeddings. So that means we can compare them. But before comparing them, of course, as before, we normalize them. So we should normalize them again here. And yep, same process again, and we can see that those have changed. Okay, cool. So what we now want to do is calculate the similarity between all of our image embeddings and all of our text embeddings. So we can do that in a few different ways. We have cosine similarity or dot product similarity. The reason we can use dot product similarity is because we normalize. But I'm going to show you how to do both, so that if you don't normalize, you can actually just use cosine similarity like we do here. So cosine similarity is actually just a dot product as a numerator between the text embeddings and image embeddings, and in the denominator we have just normalized the norm values of both of those. Okay, that's all it is actually. So it's pretty simple, and if we plot those similarity scores between those, we get this. So we would expect, along this diagonal here, we would expect these to be the highest similarity values because they represent the true pairs, okay, between the images and the text. Now we have some that are not quite there, like here. There is this image text pair which is more similar even with something else. I very quickly put these together, so they're not always going to be perfect. So we have one here that is maybe not perfect, but again, there is also a lot of overlap between these images. So there are several images of city skylines, and a lot of the time I describe those as futuristic cities in whatever, with a big motorway or something along those lines. So that is probably where we're getting that from. Now, if we were to calculate the dot product similarity between these, we would expect it to be the same. Okay. Now, from this calculation of dot product similarity, we do seem to get a very similar set of similarities at the end there. But are they the same? Well, if we go down here, we can see that they pretty much are. So we can't do a straight comparison. We can't do cosine similarity equals dot similarity, because the numbers are actually slightly different, but they're only slightly different because there's sort of a floating point error, because these are all floating point numbers. So we get very, very small differences between the numbers, and you can see that here. So we've calculated the difference between the numbers in the two arrays, and then we're looking, okay, what's the minimum difference between them? It's 0. Okay, that's what we'd expect. That's where the numbers are exactly the same. What's the maximum difference between the numbers? And it's 2.98 to the -8, so like 0.00000, and so on 2. So very small number. And okay, with that, we know it's just floating point errors between those two similarity arrays. So that's pretty cool to see that. And we can use this exact concept of comparing with a cosine similarity or dot product similarity to actually search through all of our images with like a text prompt, for example. But that's not all that CLIP is good for. CLIP also has this amazing performance as a zero-shot model for different tasks. Okay, so not even just one task, but actually different tasks. So it performs incredibly well out of the box for classification, and we'll go through this in more detail in a future video. But the idea is that given a set of classes from a image classification data set, you can modify them a little bit, the class names, to make them more like a sentence. And then you use this same idea of comparing all of your text representations of the classes with a set of images from the dataset. And with this, you just calculate the similarity between those, and the text embedding, or you can think of it as a class embedding that gets the highest similarity to your image, is the predicted class. Okay, so you have zero-shot classification like that, super easy. Another use case is object detection. So let's say you have, maybe you're looking for a cat or a butterfly in an image. Okay, and when you're looking for the cat, you're gonna use a chunk of text that says a fluffy cat. Okay, and you encode that with CLIP and you get your text embedding. And then what you do is you break up your image into all of these little patches, and you just slide through all of those patches. Okay, you can include like an overlap, so you're going over you're not missing anything between patches, so you're just sliding through your image. And with each part of the image that you slide through, you extract the image from that, you process it through CLIP, and then you compare the encoding for that image against the text that you create, so a fluffy cat. And what we will see is that patches of the image that contain what it is you've just described will have a higher similarity rating. Okay, and then you can overlay those scores back onto your image, and you will find that that CLIP is able to essentially identify where in your image a specific object is. And you are just describing that image using a natural language prompt. Now, these are only a few use cases of CLIP, and only really scratch the surface of what is actually possible with this model. We also see it being used in, like I said, the diffusion models like DALL-E, which is a great example of how powerful CLIP can actually be. So that's it for this introduction to CLIP. I hope it's been useful. As I said, we're going to go into more detail on the different use cases of CLIP and how to apply CLIP for these use cases in future videos. But until then, that's it for now. So thank you very much for watching, and I will see you again in the next one.